Okay, so we have derived now a formula for finding out shear stress distribution through the thickness. So now we'll try to see its variation. How does shear stress vary through the beam depth? So this I have shown this. This is the B and this is H of the beam, and so on any cross section of this beam here, that I think diagram I have drawn is slightly smaller. So you have a shear, let us say shear force here V, and of course moment also is there, something is there. So on a cross section of the beam, now I'll draw a bigger, let me draw a bigger depth beam. This is the neutral axis, this is the longitudinal section X, and this is the width of the beam, this is the depth of the beam. Okay, this is distance Z. So this distance is Z. And we are talking of this small area on which this is the longitudinal. So you have a sigma x here acting, and you also have a shear stress component tau xz at the same point. So both are now acting. There is also a normal stress on the cross section, there is also a shear stress tau. Value of tau can be given by this. Normal stress sigma is given by mz by I. So this variation you already know, sigma x variation is triangular. It varies linearly through the depth, positive and negative. And then this one, now we have to find out this tau. So you see in this formula, V is constant on the cross section, moment of inertia is constant, width of the beam is constant. So this tau at any cross section, see, first of all it is a function of V. So it will be different at different cross section because shear force will be changing along the length of the beam. So it will be a function of x along the length. But for a given section, for a given section, V is constant, moment of inertia is constant, width of the beam is constant. So only Q, and Q is given by Q is given by YZ dA. Or area A1. What is area A1? No. Area A1 is what? BZ, DA is DZ. DA is BJ. DA is B DZ. This is B. So DA is B DZ. And what is A1? A1 is area above this Z, this total area. This total area is A1. This hatched area. Have you understood or not? Now here at the top, shear stress will be 0. Why shear stress should be 0? Because it is a free surface. There is nothing on the top. Here there is nothing. So no normal stress, no shear stress. Here sigma is 0. Sorry, sigma is not 0, my dear friend. Sigma z is 0. Sigma x is not 0. Sigma x acts on this plane. So here sigma z is 0 and tau is 0. Here again tau is 0. So top tau will be 0. So we have to find out Q. So what is Q? Q is, now for this section, area is B dz into z, and we have to go from z to h by 2. This is going from z to h by 2. Why? This distance half is z by h by 2. Depth is total h. This total is h. This is h by 2. This one is h by 2. So going from z to h by 2. तो देखिए क्या हो रहा है. B is constant. Z dz means z square by 2. Going from z to h by 2. So that is equal to B. 2 you take outside. 2 can be taken outside. Z square by 2. Yes. Z square by 2. So it will be h by 2 whole square minus z square. When z equal to h by 2, it is 0. When z equal to h by 2, so when z equal to, I think go to the next page. Zero. So that means our formula is okay. When z is equal to 0, Q is equal to, when z equal to 0, Q is equal to B by 2 into h square by 4. So BH square by 8. When z equal to minus h by 2, means at the bottom, when z equal to minus h by 2, z, now we are coming down. We are changing the sign. We are coming here minus h by 2. When z equal to h by 2, then this quantity, z equal to, what is it? Yes, when z equal to h by 2, then it became 0. When z equal to 0, then it is bh square by 8. And when z equal to minus h by 2, again 0. Yes, very good. So Q equal to 0. So maximum, this value is maximum. In between it varies, in between top and bottom, it varies parabolically. What is the variation, by the way? So if this is the depth, top, bottom of the beam, this is the mid. So this is equal to BH Yes, this is the top, this is the bottom. Any question? So shear stress distribution means the shear stresses through the thickness vary parabolically and its magnitude varies in this way. Actually, the shear stress on the depth of the beam, if this is the beam, this is the depth, so it will be maximum here. Maximum means I will show it by a very big arrow. This is the shear stress of this much length. Big arrow. As it goes up, a smaller arrow. It goes up, further smaller arrow. Goes up, here it becomes 0. No shear stress. Comes down, and here it is 0. Okay? Is it okay or not? There is no sign change. Plus से minus नहीं होता है. It is the same vertical. And if you integrate all this shear stress over the entire area B into dz from top to bottom, then what will you get? Quickly, when you integrate this shear stress over the area of the cross section of the beam is like this. Cross section of the beam is like this. This is the cross section. This is B, this is H. V, yes. When you integrate, so you get, when you integrate over the area from minus h by 2 to plus h by 2, B multiplied by tau into dz will give you V. B into dz is the area multiplied by tau. So this is area multiplied by tau. That will give you shear force. Clear? So this will always be holding good. But its variation is like this. Shear stress. Now that is a rectangular cross section. Shear stress varies like this. It has to be 0 here because the top and bottom are free surfaces. It cannot be anything other than 0. Then what about, I think last time I had asked you to find out normal stresses for different sections, cross sections. I did it for rectangular, then I told you, you do it for I section and then T section. How many of you did it? If you keep it only for the test, the previous night before the test, you better do it. Now let me take a cross section which is like this. Now you can see physically, you can understand. Let us say there is a cross section which is T section. And on this you have a shear force V. I want shear stress distribution. At any cross section, there is a shear force V acting on this cross section. This is B, T, T, H. I can only tell you that shear stress distribution will be yes, how will be the shear stress distribution? This is the, I want to know shear stress variation as a function of Z. Shear stress variation means like this. any constant z, it will be having the same value across the entire width. Any constant z along the width, it must be same. Shear stress per unit area, it must be same. This magnitude must be same at any z. So here at this level, supposing you want in the width direction, its magnitude must be same. So yes, what is this variation? Qualitatively, I will tell that here it is T is changing, thickness is changing. See, what is shear stress formula? Tau equal to V by IB into Q. Now here B is not, so V is constant, I is constant, Q by B now will be changing. B is also changing. Width of the beam, here width of the beam is this much, here width of the beam is this much, here it is the same. So in this flange, this is called flange. Do you know this? This is called flange of I-beam? No. You don't know. You know this is I-beam, it looks like I letter, capital letter. So this portion is called flange. From the same cross section of rectangle, what we have done, we have removed the material from the rectangle. This was originally rectangle like this. What I have done, I have removed this. So it has become T. So this one is called flange, F-L-A-N-G-E, flange, and this portion, this thin portion again is called web, web of the beam, web. This is web. So the wider portion is called flange, and the thinner portion and the deep portion is called web. So in the web depth is this much. So this is your web, from here to here is web, and from here to here is flange. You can do the same thing. Supposing I am here, I take my Z here. So I will have to take Q. I will have to find out Q for which area? Area above that line. What is Q? First moment of the area above that line. No, I think I don't. Supposing I want to find out stress at this level. So this is my. So what is the area above this line is this. So first moment of this area total. First moment of the area. How will you find out first moment of the area? Qualitatively or quickly. What is first moment of the area about this line? Area multiplied by distance up to the centroid. Up to the centroid of this. That is a simpler way to find out. First moment. Moment of the area will be what? Integral means what? Integral is ZDA. What is Q? Q is ZDA. So this is nothing but total area multiplied by Z bar. Is it okay or not? Yes. From centroid formula, from center of gravity formula, total area multiplied by Z bar. Z bar is the distance from this axis to the centroid of this. So the shear stress at this level will be that. So you can find out, yes, the distance will be centroid, means it will be h by 2 minus t by 2. This distance has to be reduced. See, it will involve computation. You cannot say. So I will say here, let us say at A level, tau xz, at A level, tau A, at that level, what will be the value? It will be equal to V divided by I divided by, what is the width? There B is this total B. You are in the flange. Supposing you are slightly in the flange. See, not at the junction, slightly inside the flange. So then it will be B, and Q value will be equal to area of this. Area of this is how much? Area of this is B multiplied by this is how much? This is B into this is how much? T. B into T. And distance from centroid will be equal to how much? H by 2 minus thickness is T, so minus T by 2. Is it okay or not? How many people understand this? Yes. Shear stress at level A in the flange is given by this expression. You can integrate, you will get the same thing. Quickly tell me yes or no. So this you find out the value. This you find out the value what will be. Now at A level, but now I am in the web. I just come slightly in below at A1 level. So tau A1 will be what? V by I. I'm just trying to explain to you. This is in the flange. So this was in the flange. A was slightly inside in the flange, not at the junction. See, it is a junction. Changing area is, width is changing suddenly. Suddenly it is becoming from B to T. Sudden jump is there. So either you are in the flange or you are in the web. You cannot be in both. You cannot be at the junction. Whenever there is a change anywhere, so you decide which side you will be there of the boundary. If you are in two districts, there is a boundary line. Either you in Satara or in what is the next district? So you cannot be on the boundary. So this is, now this one will be equal to 1 by, here it will be T. This one will become T. Mind it. Width here is T. Then first moment of, but then this will not matter. That will still be remaining Bt into H by 2 minus T by 2. There is no change in this. So what has changed suddenly? What has changed suddenly? This is B, this is T. So this value will be, which one will be more? T is a smaller quantity, so this quantity will be more, and B is a larger quantity, so this quantity will be less. Yes, this is less. So from small to suddenly it will jump. So I will now draw the shear force diagram or a shear stress diagram. So this is the junction. It will start as usual, if you find out here, because here area above this line is 0. Q, value is Q. At this line, what is the Q? Q means first moment of the area above that line. At this level B. Why are we saying that shear stress is 0? Because one is free surface, but mathematically the value of Q here is 0. Why? Because Q has to be above this, area above this line. What is the area above this? There is no area. So Q is 0, so it is 0. So it has to start from 0 and then it will vary quadratically. This function is quadratic. It is Bt square, B square, whatever it is. Okay. So this will be varying like this, quadratic. So it will come to this value B. Then suddenly in the ratio of Bt, it will become large at junction, because this has become small. So in the web, it suddenly jumps. Do you understand or not? Denominator has become small, so value will become, tau will become more. This quantity has become small, so T1 will be more than TA. Okay, so this will jump here. Again, from here, now width is remaining same. B is remaining same in this web. This B is constant. No change. So it will be only area above this, moment of the area, Q. Q is the moment, first moment of the area. So that will be again varying quadratically, and it will vary like this. Please find out yourself and you get this variation. I am giving you qualitative. So this is parabola. This is a jump. Again this is parabola. And maximum will become here at the center. As before, maximum will become at the center. Again it will be symmetric. It will come here. There will be jump down and then like this. So shear stress distribution. So this is the shear stress distribution. These are the ordinates. These are the magnitudes. This diagram shows the magnitude of the shear stress. So here you can show it by a bigger arrow, a smaller arrow, a smaller arrow. Here it will be bigger. In the web it will be bigger. Suddenly in the flange it becomes smaller. And it becomes 0 here. Do you get it? Vertical. All quantity will be vertical. So shear stress diagram in T-beam. This is very important. You should be able to plot this. So please write down the expressions and do practice. You do practice. Do you get it or not? It will be symmetric. Just like rectangle, it will be symmetric. Please find out also for another cross section. Huh? What? What has happened? Please find out also for another cross section, and that is this unsymmetric. Next example. Example T section. See, your bending theory applies to any cross section which has a vertical plane of symmetry. So it applies to this also. T. Whatever we have developed applies to any cross section which can be divided into two halves like this, vertical. This Z will divide into two halves. So T. The only thing its centroid will be somewhere here, G. So neutral axis, this is Y and this is X. Sorry, this is X. Please find out and plot the variation of shear stress in this. Now unless you do some homework, some exercise, some computation yourself with the help of your own, you will not understand. Everything cannot be done in the class. And don't write the comment that no examples were solved. Yes, what will be the variation here? Qualitatively, not numerically, not quantitatively, but qualitatively. It has to be 0 here, bottom, 0 here. Okay? Again, there has to be a jump. See here, if you are in the flange, by the way, this is also called flange. This has got only one flange. This is a T section. Has got one flange and this web. This is web. So anybody will be guessing how will be the variation? Tau. As before, As before, it will be maximum at the neutral axis. Value will come out to be maximum at the neutral axis. I don't want to do the calculation, but then it will be again parabolic, 0 to this in the variation. B will be this B, VQ by IB. So B will be this, then suddenly B changing, nothing else. Is it okay? This is all right? Then what will happen at the junction? Jump. Why it will be jump? Because B is changing, B is reducing. Suddenly here B is becoming this much. Here the B was this much. So everything remaining same, only B is, area is remaining same. So first moment of the area will remain the same, but then only B is changing. So again there will be a jump. It will come and then it will become maximum here. It will come and maximum here. That you please write down, derive the formula Q expression, write down the expression for Q and do it for every ordinate. Okay, only Q is only Z is the variation, nothing else. And then it will vary, it will come again. So this also will be parabola. So a parabola, I see it is like this, maximum here. I think maximum, if I am not wrong. Yes, it has to be maximum there. Jump. So shear stress distribution will be like this. So it will be like this. Just see here, 0, some, slight increase, slight increase, slight increase, slight increase, and here it will be maximum, again smaller, 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 and then 0. So here all like this. This is the vertical shear stress. Vertical shear stress. Okay. So now quickly, fourth. Yes, sir. What is tau A1? What do you mean tau 1? क्या हो गया? Yeah. What is the problem? Above, see wherever the line, because Q means, see, this is the total Q, any area is there, cross section is like this. What is, how you have defined Q? Q is this area of this, and this is the neutral axis. This is neutral axis. This is Z. The Q is defined as, this is the area. So Q is first moment of this area. First moment of the area is also equal to area multiplied by distance to the centroid of this from here. Z bar. Z bar is the distance from here to centroid of this area only. Centroid of this area. I mean, that is the basic center of gravity theorem. First moment of the area, if I integrate, that can be also found out as centroid multiplied by the distance to the, multiplied by total area. बस और कुछ नहीं. Width is changing. Yes. Anywhere, yes, here width is changing. Area which is above Z. Area that is above Z is Q. Q is this. Q is ZdA, which is equal to total area multiplied by Z bar. How do you get center of gravity? Center of gravity is ZdA divided by total area. So that can also be written as A multiplied by, where A is this area, this hatched area is A. So this is a general, so please practice, this is important. Bending and shear stress is an important chapter, and this again you require it not only in this course but throughout your life. You have to find out bending stresses, shear stresses in many situations, and you will be using these two formulae. Now I will solve a simple problem, an example. So I will take it as if bending stresses and shearing stresses are completed. Okay. Don't tell me this is, I will take a simple problem. This is a problem. There is a beam. I am doing this because you have given me a comment that you don't solve problems, but problem means I think you mean unless it is numerical value, unless there is some newtons, kilonewtons, meter, centimeter, so that is problem. So okay, so we'll try to solve a problem. So this is a beam with overhang. This is called overhang. It is cantilever, overhanging. In buildings, this will be your room and this will be your balcony. But balcony on both sides. It is luxury in Bombay. So 5 kilonewton. Most people cover the balcony and make it a part of the bedroom. Hmm? 0.3 meter. Everything is in meter. Yes, please. So what is the bending moment diagram? What is the free body diagram, first of all? This is in kilonewton. There will be reaction here, there will be reaction here. What will be the value of the reactions? Quickly. 5. This is in equilibrium, and therefore the bending moment shear force diagram would look like yes, 5 into x, 5 into 0.3, so 1.5. So this will go like this. This will be 1.5 kilonewton meter. Kilonewton meter moment. Yes or no? Then from this side also it will go and meet in the same matter. And then in the center it will remain constant. You can check, you can take any section and check. So this value will be 1.5 kilonewton meter in the center, and it is changing from 0 to, this is the bending moment diagram. This is the bending moment. And shear force is yes, please, shear force. Shear force will be 5. This value is 5 kilonewton. 5 kilonewton. This from here to here. Got it? then here it will be negative. So this will be negative, this is positive, and here it is 0. Shear force here is in the center is 0. So it varies from positive 5 kilonewton 0, and then again this is the shear force diagram V. This beam has a cross section which is rectangular, and B and H. B is 25 millimeter and H is 75 millimeter. So what is needed? I want to find out first what for this problem is being solved. We want to find out the maximum stresses that have developed in this beam. Of course, maximum bending moment, maximum shear force, and then the maximum stresses. Because the stress anywhere in the beam should not exceed a permissible value for the material of which this is made of. There is some permissible. How do you get permissible value? What is the concept of permissible value? You have to divide yield divided by safety factor. 1, 2, 1.5, let us say factor of safety is 1. This is a simple way. Yes, so yield, because material starts yielding, it starts going into plastic zone. I don't want material anywhere to go in plastic. It stresses to reach yield point. So what is your best way? You see that nowhere it goes beyond yield stress divided by 1.5. If you know more about the material, if you know very well, then you give a smaller factor of safety. If you know less, then you give less factor of safety. So for example, steel, it is given about 1.5. For concrete, how much it is given? Anybody? 3. 3. Factor of safety is 3 for concrete structures. You know, because concrete is a very complex material. You manufacture concrete on the site with labor, they are unskilled. You have to mix sand, cement, aggregate, mix water, then mix it, place it. You will tell them that you put this much water, they will put little more than that or more than that. So the whole stress, everything changes. So we give a factor of safety of 3 for concrete. Okay, so we want to find out. So in order to find out, the first thing that we have to find out is what? Please show all these axes. Whenever you draw any problem, please show the axis so that there is no confusion. This is what I show it. Cross section I draw it, then I show Y and Z, and in the longitudinal I will show it my X like this. So I have to find out all these things require Y. Moment of inertia of the cross section is always required for finding out the stresses. So moment of inertia is how much? BH cube by 12. Rectangular cross section. And before going into, so how much it is? BH cube by 12. B is 25. H cube 75 cube by 12, and that turns out to be 8.789 into 10 to power of 5 millimeter raised to the power 4. This can also be written as 789, and then 1000 millimeter makes 1 meter. So if you want to write down in terms of meter, so you have to divide this by -7. You are quicker than me. Yes, -7. Meter 4. So this, now if you make mistake in these things and then you say, sir, I have done everything wrong or everything right, but here I have made a mistake. No, it is not permissible. You cannot make mistake. If you are an engineer, everything else will be wrong, So you don't deserve. And that is why I think last time you did not get marks for some problem. You have made mistake. Many people complained that yes, they have done the problem, method is okay, but you will not get marks. Okay, so moment of inertia is done. Next is what? So first thing is geometry you must know, loading you must know, length you should know, then you should go to 6, 5. This is 6. This is 6. Now bending stress, sigma x. Maximum bending moment is how much? Yes, so maximum occurs, so maximum bending, so sigma x maximum equal to m maximum into c divided by Iyy. By the way, this is also called m maximum Iyy by c is called section modulus, and it is denoted by a letter z, and this is called section modulus. Section modulus. This is a fixed quantity for a given cross section. Moment of inertia divided by c. C means h by 2. C means h by 2. Maximum. So this is a fixed quantity, and these for all the steel sections are tabulated in steel handbook. You will be using in next semester steel design. So there is a handbook where for I section, T section, the section modulus for various flange widths and various depth, they are all tabulated. The ones which are made in steel factories, steel mills, standard sections are made and they are all tabulated. The Z value will be given to you. So they are all known. You don't have to compute. They are there in handbook. So section modulus it is. So you should know this. What is section modulus? Section modulus is Iyy by c, maximum h by 2. So this in our case it becomes 1.5 into 10 to the power of 3 Newton, kilonewton is it was there now, so I am making it Newton meter, 10 to the power of 3 I have multiplied, is it okay? And into C, sigma x, डेप्थ कितना है भाई? 75 का आधा, how much is half? 37.5 into 10 to the power of 3 minus 10 to the power of minus 3 meter. So everything in meter, Newton meter, I am writing everything in Newton and meter. So this is an 8 point. Best thing is to write the units. So you get here 64.0 mn. What is mn? Meter square. What is mn? Mega Newton. Mega is how much? 10 to the power of 6 Newton. Check up. So this is 64 into 10 to the power of 6 Newtons per meter square. Please check up. So this is, I just wanted to tell you, this is how it is computed. Now what is, supposing I want to find out what is the radius in which the beam has bent. After all, beam has, there are two loads that are applied at the ends, and beam must have lifted like this. This is the very exaggerated, here is the support and here is the support, and this is the load and this is the load. So it is bent, and of course we are talking of radius at the center because this is constant moment. This from here to here is subjected to constant moment. So here the radius will be R. Here it will not be, it will be different because here this is also subjected to shear force. Here but constant bending moment. So this is R. So please tell me how to find out R. R is equal to d phi by ds. R equal to 1 by R. 1 by R equal to m by EI. Curvature is given by m by EI. Yes. It is like this. 1 by R curvature, I think you have m by I equal to E by R. I think we have derived the formula. So 1 by R curvature is given by m by EI. So please put all these values and you will get the value of 1 by R. So 1.5 kilonewton meter divided by E. E is given here as 205 into 10 to the power of 6 kilonewton meter square. That's it. And that multiplied by I equal to 8.789 to 10 to the power of minus 7 meter 4. So this comes out to be 8.325 into 10 to the power of minus 3 radians per meter. 1 by R. Radian has no unit. 1 by meter. How is this d phi by, I think d phi was coming because of this. And we were taking ds, this is ds. D phi by ds. So radius also is found out. Then supposing we want to find out yes. Supposing we want to find out what is this value d phi. Anyway, R is known now, so we can find out. Supposing now we want to find out what is the value of this angle. So R is known, so we can find out this. So d phi will be equal to from A to B will be equal to A to B m by EI into ds. This you integrate, m by EI any we have found out, and ds is 1.5, so it is 8.325 into 10 to the power of minus 3 into 1.5 meter. So this comes out to be 0.0124 radians, and that is equal to 180 divided by pi multiplied by 0.0124. So that is phi, angle phi AB is equal to 180 divided by pi into 0.124. 0.124. What was 0.124? 124 was radians. That was coming. Yes, so many radians. So this is in degrees, and this comes out to be 0.72 degrees. Supposing you want to find out R, of course 1 by R you have found out, so 1 by R was how much? 1 by R was equal to 325 into 10 to the power of minus 3 radians per meter. So that is 120 meters. So everything, it is possible to find out all the geometrical quantities, but then you have to go systematically. So this radius is 120 meter of this, under which this beam has bent. Okay, you have known now all the computations. So bending of beam under both pure bending as well as under general loading. Now you can find out everything. Now these bending stress assumptions are very important. Derivation of formula is very important. Don't think that in the examination only problems will come and no derivations. So derivations may come. So don't think so. Derivations are important. And now there is one small section that has remained. I will just give you. I will not going to take it. Supposing there is a simply supported beam, you go on loading in the center. What will happen? Stress will go on, bending stress will go on increasing. Bending moment will go on increasing at the center. Maximum bending moment is occurring at the center of the beam. A time will come when the maximum stress of the fiber, extreme fiber, will become equal to yield stress. But it will be only the top fiber and bottom fiber. Now you can still load, because that has become plastic, but inside of the beam is still elastic. So load it further. So now plasticity will start entering through the depth from the outer edges. So it will start becoming plastic till the entire cross section becomes plastic. Now what is the stress that will be there when it becomes plastic? Maximum stress. The maximum stress, it can be only sigma y. It cannot go beyond sigma y. See, ultimately you are getting a triangular loading during elastic. But once the extreme fiber is becoming plastic and then the bottom fiber starts becoming plastic, so that value will remain equal to sigma y only, yield. So what kind of stress diagram you will get? Rectangular. Top rectangle and bottom rectangle. And stress will be constant sigma y and sigma y. And entire cross section has become plastic. When the entire cross section becomes plastic, what will happen to the beam? Entire cross section becomes plastic. Let us say it starts bending. Ultimately it will become like this. At the center it will become, see, it started like this. Now so far it was elastic, so it was having some elastic curve. But the moment it becomes plastic, fully plastic, it will become two pieces, one here and one here, and it will, so there will be two pieces like this, and because the center cross section has become plastic, maximum entire. So that is called fully plastic section. The complete capacity of the central cross section has been reached and it cannot be loaded any further. It will collapse. The beam will break into two pieces. Okay, center it will become a hinge. Center will be something like a hinge. It will be like this. The two pieces, supposing this is the center. This is the center. So plastic means once the load becomes, there will be some elastic curve like this. Now hence the entire becomes plastic, it will become like this. It will become, so from here like this, triangle. And we say that at that level, a plastic hinge forms at the center. So it becomes it is not a physical hinge. See, at the two ends you have got a physical hinge, a pin. Here it is a plastic hinge, which can rotate freely because the material has become fully plastic. But at the plastic hinge, there is a moment acting because the stress diagram is there. So moment is again constant, and that moment is called plastic moment. So I will tell you about this in the next class on Monday. Yes.